Hello everyone, welcome to the next episode of this video series on wireless strain gauge design and development. Part 2, we will be discussing about full bridge, half bridge, and what is an amplifier when it comes to designing a load cell. So in today's video, the following topics will be discussed. Firstly, we go back to what has been covered in the previous episode. Then we will narrate on the design consideration, especially on temperature variance and its effect on our load cell accuracy and some of the wheatstone bridge principles. Then we will say what is a half bridge and a full bridge wheatstone bridge. In the fourth part of this video series, we also talk about what is the need for an amplifier, and we will also answer some of your frequently asked questions in part 5 and plan out for the next video in the last part. So in the previous episode, we have laid out the foundation for a load cell design and why it is needed in construction industry. A load cell, also in some context known as a strain gauge, is an instrument that converts deformation into electrical signals, which can again be converted later on into load values measured in kilonewton, kilogram, or any other relevant unit. So if you're working in civil engineering or any part of heavy duty industries, you definitely work with load amounts, kilonewton, kilogram, and you know that reading a load amount can help you a lot in your daily operation. So the component that makes these measurements available is called load cell, and it has been also covered in the previous episode. Load cell has a wide variety of applications in civil engineering, such as live health monitoring, dosing, batching, haulage, and so on and so forth. In today's video, we will be talking about design considerations of a load cell, such as temperature variance and accurate measurements. If you remember from the previous episode, um, load cell are basically a really long, tangled, conductive material that deforms as the load is imposed on it. And the deformation, based on the Ohm's law, would change the resistance of that conductive material, which that change in the resistance can be converted into voltage changes, and that voltage change can be converted into a kilonewton value or a kilogram value. So uh, the basic of load cells relies on the Ohm's law. And we all know that the conductance of a conductive material would change based on the temperature change. So if the temperature rises, the cross-sectional area of the conductive material would change, and that would affect the final reading. So in order to mitigate that change and make temperature variance somewhat redundant, and make our readings always accurate, there are some steps that we can put in place in order to avoid any errors in creating the numbers. Half bridge and full bridge relies on the wheatstone bridge principle. So in this picture, you'll see a wheatstone bridge. So Rx, for example. So let's go back a bit. R1, R3, R2, and Rx are all resistors. Rx is our load cell or the strain gauge, and other ones R1, R3, R2 are other types of resistors. So for a bit of compare, what we are doing when measuring a load, we are comparing voltage changes, Vg, which changes over time as we load and unload the scale, let's say, or the health monitoring system. So a half bridge con- is composed of two strain gauges. A full bridge is composed of four strain gauges. So on the left hand side, you see a full bridge, which has all the four resistors in place and connected to something called amplifier. Like green electronic board you see is an amplifier. In the next slide, we will discuss what is an amplifier and why it is needed. In the middle picture, you'll see a half bridge where there are only two changing resistors, and combined together, it would generate a signal, send it to an amplifier, and it will be sent to a microcontroller later on to be analyzed. And on the right side, there is only one, or it's also called quarter bridge. There's only one changing resistor, and there is a necessity to put two external fixed resistors. You see this 1K, these are external resistors. It is not recommended to use only one strain gauge in a load cell because when the temperature changes, this can cause error in the reading. So the highest accuracy normally comes with four strain gauges in a load cell, what you see on the left side. And also the second one is also acceptable. A half bridge is also a form of an acceptable load cell design, but the right side circuit design is not accepted. Although it works, but be aware that when temperature changes, your readings will be totally faulty. Now, we also use something called amplifier. HX711 is a pretty common used amplifier, but we need to know why there is a need for an amplifier in a load cell. The need for an amplifier like the HX711 comes down to signal size, accuracy, and ease of interfacing with microcontrollers. Strain gauges and load cells produce very small voltage changes, typically in the microvolt to millivolt to millivolt range. A typical load cell output is 1 to 2 millivolts. So if powered at 5 volt, for example, the maximum signal is around 10 millivolt. Microcontrollers like Arduino or ESP32, these are the DIY microcontrollers, cannot detect such a small voltage changes accurately using their built-in ADC. They are designed for only 0 to 5 volts, and basically what an strain gauge produces cannot be read by the microcontroller. So in order to read those signals sent by the strain gauge, we need an amplifier. And HX711 amplifies the signal up to almost 10,000 times more, making it readable for commonly used microcontrollers. So that's why we need an amplifier. Another frequently asked question is that can I make a full bridge with a two-wire strain gauge? So on this picture, that's a typical strain gauge. It's a long length of tangled conductive material that deforms as load applies, and it normally connects with two wires. And the answer to this question is that a two-wire strain gauge by itself cannot directly form a full wheatstone bridge because it only acts as one variable resistor. So again, we can go back to two slides. We can go two slides back and see what was the quarter bridge, which is not producing any accurate measurement for us. So a full bridge requires four resistive elements, typically four strain gauges wired in a specific configuration, which was shown previously. Another typically asked question is that, so is it fair to say that the two strain gauges will make a half bridge and an HX711 the other half, and altogether they make a full bridge? And the answer is no, because it's not accurate to say that the HX711 makes up the other half of the bridge. What the HX711 or the amplifier do is that it just amplifies the signals that are received from this strain gauge. It does not contain any resistor or internal circuitry to act as part of a wheatstone bridge. It requires a full bridge to function correctly. So if you have only so let's figure out what kind of scenarios are available. To make a function in setup, you must build a full bridge externally using two strain gauges plus two precision resistors. So if you only have two strain gauges, you have to add two external resistors. Or if you have four strain gauges, you already have your full bridge. Congrats, you can just connect it to the amplifier, and from amplifier to the microcontroller. Or if you have one strain gauge, you're going to need three resistors to create that full bridge. So this configuration is also called a quarter bridge. And then the HX711 is powers the bridge via its E plus and E minus pins, and reads the differential voltage from the A plus and A minus inputs. Next, we will be covering the wireless communication protocols and RFID systems, and it will be our next episode of this video series. It will be interesting to know how to send those signals that we have received from strain gauge to somewhere remote without um, a need for a wire. It will be communicated wirelessly. Thank you so much.